Idag har vi med oss Lars-Johan Sandström från Luleås tekniska universitet och Sayed Salehi från Chalmers. Och de kommer presentera varsitt projekt här nu under den kommande halvtimman. Och sen så har vi även med oss Jonas Karlsson från Juniper som är vår expert och vår industrirepresentant för dagen. Och han kommer ställa frågor till Lars-Johan och Sayed i slutet här på webbinariet. Nog med introduktion, nu ska jag byta till engelska för att dagens presentationer kommer att hållas på engelska. And the first speaker of today is Lars-Johan, and you will present your project Condition Monitoring for the Identification of Behavioral Changes in Hydropower Units. The stage is yours. Welcome.
Oh, yes, thank you. Thank you. So now I will start with trying to share my PowerPoint here. Yeah, okay, great. Yeah, my name is Lars-Johan. I'm a PhD student here at LTU, and my work is in with condition monitoring or automated turbine monitoring. So today I will talk about two cases that we are working on. So I will talk about the case about efficiency monitoring that we are doing and sensor evaluation that we have done so far. And I will also talk about some friction monitoring of the Kaplan runners in the Kaplan turbine. So I thought I'd start with efficiency monitoring. So to achieve this good efficiency that we have in the Kaplan turbine, it's recommended that every 5th year or so that we make this index performance test where we basically set the runner blades and guide wine angles in proper positions to achieve a good efficiency. And this is done by when we are basically setting the runner blade in a fixed angle and we letting more and more flow into the turbine and we measure the efficiency at the same time. So you can see here on the one propeller curve we have a fixed runner blade angle and we are letting more and more water into the turbine, and then we get one point where we have the best efficiency. And then when we do it on different runner blade angles, we can get this Kaplan curve where we have the best efficiency. And this is more or less programmed into the system that runs the turbine. But if we have some problems with, for example, sensors that are measuring the water levels in the dams, it can offset this curve. So in the end, we don't run under the best efficiency that the turbine can have. So what we're trying to look at here is can we have some other parameters that we can relate to the efficiency of the plant that we can measure without measuring the flow into the turbine. So that would mean that we can also measure it during production. So in the first case, we have here looked at some sensors that we equipped on the Vattenfall's test rig in Älvkarleby. So in this first case, we only have looked at a single propeller curve, so one fixed angle of the runner blades and varying angles on the guide vanes here. And we equipped it with additional accelerometers on the locations that I show here, so near the turbine and on the guide vane axis, and also on the lid of the turbine. And what we're trying, we also put an acoustic emission sensor here near the turbine as well. And what we're trying to do here is to predict the guide vane angles from this accelerometer data. So if we can say where on this curve we are, propeller curve, from the accelerometer data, we can also say that maybe we want to lie in this sweet spot where we have the best efficiency. That's the idea of this experiment. So at the first stage, we have made some feature evaluation. And here we use neighborhood component analysis, and this is to tell us which of the features that are most relevant for predicting the guideway in opening. So then we get the plot that looks something like this here. So we can see that the mean value and standard deviation and also skewness and crest factor seems important for this accelerometer. And then we do some regularization, and with that we mean that we only more or less trying to only keep the most important features to the model. So it has we're only trying to take as few features as possible you can think of. From this we could see that all the different sensors worked to predict the guideway angles, and we have some variations with the sensor axis and also on the placement of the accelerometers. From this plot, you can see that if we look at the blue crosses here, the position here near the turbine seems pretty good, and also if we look at these two values, this is on the guideway axis up here. Also seems like the most promising so far. But this is only for one propeller curve so far, and we'll get more propeller curves for other power outputs later on that we will try. So for now, in the end, we want to be able to do this over the whole power range, so we more or less can get a plane of vibration versus efficiency over the whole power range. That's the idea. And then we can detect if the efficiency isn't as good as it should be. Then I thought I'd talk a little about friction in Kaplan runners. It's another case we have been working on together with Uniper. So here we have a Kaplan turbine where they suspect that they have a friction increase that's not beneficial or not as it should be over time. And overall, you can say that hydropower turbines or Kaplan turbines have a lifetime about 40 years or so. But here they think they experience problem a lot earlier than that. So what we're trying to do here is to isolate the friction in the radial bearings here on the Kaplan runners. And to do that, we have been looking at the differential pressure. So here is a simplified sketch of the system. So we have the Kaplan runner and a radial bearing, and we have some piston that regulates the runner angle. So here you can think of the differential pressure is I defined it like the closing pressure minus the opening pressure. So the difference in pressure between the sides. And if this differential pressure increases over time, or the absolute value, it can mean that we need to put in more work or more force to move the runner blades, which could be an indication of increasing friction in the system. The differential pressure is affected also by other features, but increasing friction can also be one of them. So if we look at the data first in the left plot here, here we have the power spectrum on the x-axis and number of samples on the y-axis. So if we look at the data a bit under 20%, here we have much of the start and stops of the turbine. So this data we don't analyze. We take this away from the analysis because it's hard to analyze it since the turbine can stand still, and we have this starts and stops. And the rest of the data, here we divide it into 5 power categories. And then we analyze each of these power categories individually. So if we look at power category 3 here, and we plot the closing pressure versus the opening pressure in this piston, then we get to plot something like this. Now it's many colors, but I will explain them more. We can start with that we have some knee here in the plot. So in this knee, we more or less have where we differentiate if we are opening or closing the turbine. So if we go upside here, we have a larger opening pressure, which means that we are opening the turbine, or if we go in this direction, we are closing the turbine. So what we've done here is we're trying to automate this process more. So at first we made a cluster algorithm that can divide it into this section for us. So it finds this need. That's what this decision boundary here is. And we can see that it's a little bit off to separate the classes totally correct, at least to the naked eye. So therefore, we also put in this buffer zone that we don't analyze in the models. So then we only analyze the blue dots where we clearly are opening the turbine, or where we're clearly closing the turbines in the orange dots. Yeah, so to summarize, we have first we make power categories, and for every power categories, we also separate the data into opening and closing of the turbine. So in this case, if we have 5 power categories, we have 10 models that we're working on the analysis. And for this model, we have in total 12 months of data, and the sampling frequency is 10 minutes, and we're using a linear regression model here. To the model, we put input time, the runner blade angles, and the guide vanes, hydraulic system pressure, and also a coefficient of friction that we defined, and the output, what we're trying to predict is the differential pressure. Okay, so then it looks something like this. This picture is from power category 4, so we analyze the data in this power category, and we look only at the data when we're closing the turbine. So yeah, so it's only part of the data in this model. And then we have 6 months of data that we train the model on. And what we're trying to achieve here is the model learns the behavior from a specific period of time. And then we will use this model to predict the differential pressure later in time. And if the model and the reality have huge differences, then we can say that we have some behavioral changes regarding the differential pressure. So here, okay, we trained the model on this period of time, and then we predicted here 6 months that are, yeah, it's a year later, but the same 6 months of data. So here we can see if we do a linearization of the reality and the model, we can see that the reality says that we have an increasing differential pressure of 0.2 bars here, and the model says that it's 0.3 bar. So both says that it increases a bit over this time period. And this is too small numbers probably to say anything more about if it's in what direction it changes. But the idea is to say here, if the reality says that we increase by 0.2 bars, and the model would say that we increasing even more. So that would mean that friction is increased and would have deaccelerated a little bit. So maybe we have some friction behavior and it doesn't increase as much then. That's the idea of the model. And then we do this for all the different power categories. Yeah. So the idea is here that we can detect the changing differential pressures and we can connect them to the working regime and also if we are opening and closing the turbine. We would also be possible to predict what the differential pressure would be in the future. If it's very high, then when maybe we need to take some maintenance efforts or plan for something. That's the idea. Yeah, that's all that I had. So thank you so much.
Thank you, Lars-Johan. Reminder to the audience to please ask your questions in the chat if you have any, or use the hand raising tool if you want to ask Lars-Johan a question at the end of the webinar. Now let's move on to the next speaker, the next presentation, which is Saed Salehi from Chalmers Technical University. And you will talk about your project, Artificial Intelligence for Enhanced Hydraulic Turbine Lifetime. And let's see, this is your presentation. Yes, we can see it. And you are very welcome to start your presentation whenever you're ready.
Mm-hmm. Yeah, so thank you very much. My name is Saed Salehi. I'm a researcher at Chalmers, and today I'm going to talk about our research on artificial intelligence for enhancing the lifetime of hydraulic turbines. So just to provide a little bit of context,
can I interrupt you, Saed?
Yes.
I can't see your camera. Could you please try turning it off and turning it on again? No, now I can see you.
Okay.
Sorry for interrupting.
Thank you for reminding. So so hydraulic turbines, when they work in the off-design and transient operation, they usually produce a self-induced instability. And one of the instabilities that is very well known is vortex rope, which happens at the part load condition, and that is that could be very detrimental for the lifetime of the machines. So our current research aims at firstly how to utilize data-driven methods to first provide or to get a deeper understanding of the physics of this flow, and then to use artificial intelligence to control this instability. So first, I will start with the first part, which is using data-driven methods for get a deeper understanding of this instability. And in this research, I use dynamic mode decomposition, which is a model analysis technique, and it analyzed time snapshots of a flow field to extract patterns and frequencies and coherent structures. I think many people are familiar with POD, proper orthogonal decomposition, but DMD can be seen to some extent similar to POD, but they are fundamentally different. And the important part is that DMD, unlike POD, focused on the temporal orthogonality, which means that each DMD mode oscillate with an isolated frequency, and that means that DMD modes are realistic physical representation of coherent structures, unlike POD mode that are more like mathematical representation of data. They don't necessarily represent any physics. So we looked at a case study to investigate this vortex rope with DMD. It's a swirl generator, and we used a highly resolved IDDS simulation using OpenFOAM. It's an expensive simulation with 55 million cells. We use 1600 cores, and it's around 1.1 million core hours for one simulation. And So when we solve the flow, we obtain a broad range of complex physics and interaction of these physics together. You can see here, I can, yeah, you can see here, for instance, we have the main vortex rope here, which is very similar to what happens in turbines at part load condition. We have the wakes at the trailing edge of the runner. We have a separated boundary layer here due to strong adverse pressure gradient. We have disintegration of vortex rope, and later downstream we have the reunited vortex rope. But when we perform an FFT analysis of the forces, we see that there are many different dominant frequencies or excited frequencies. The highest peak is obviously the frequency of the vortex rope itself, which is close to the frequency of the runner. In this case, usually it's around 0.3 in turbines, fast turbine coupled turbines, but here is close to frequency of the runner itself. But the important part, or the interesting part for us, was that we see some peaks here in the force that we don't know, at least initially we don't know the origin of these peaks. Of course, the first peak is 0.26 or around 0.3, and yeah, we kind of can guess from literature, and we know that it's the plunging effect or axial oscillations of the vortex rope. But the second peak, the origin of this peak is not known. And when we look at the radial force in the polar coordinate, we can see clearly that the forces are rotating 360 degrees, which means which is clearly the effect of precession or rotation of the vortex rope. But when we perform to perform the DMD analysis, we need the data. So this data is collected for 1,000 snapshots of this flow. You can see that 1,000 snapshots of is 55 million cells. It's a huge data set, and multiple terabytes of data, and it represents 17 revolution of the vortex rope. And then we only kept the data in the test section, or the kind of the draft tube of this machine to lower the cost. So when we performed the DMD analysis and we extracted the DMD modes, here you can see, for example, the strongest mode in the x equals 0, or the mid plane of the test section, and one axial plane here close to the throat. And then when we animate the dynamics of this flow, we can see that it's clearly the anti-correlated patterns here clearly are connected to the precession of the vortex rope that propagates downstream. And here we can see clearly a rotation effect. But when we look at the kind of the second strongest mode, we can see the plunging effect. So here you can see downstream the runner, there is no rotation effect. In both figures, you can see the dynamics are not in a rotational pattern, but they are in a axial oscillation pattern. They represent an axial oscillation pattern, and the frequency shows that it's the axial oscillation of the vortex rope, which is known as plunging effect. But more interestingly for us was that when we looked at one of the specific modes, that when we look at dynamics, we can see that the mode is mostly active close to the edge of to the wall of the draft tube or test section, and is very close to where this boundaryless separation due to a strong adverse pressure gradient happens. And also in the axial section, we can also see similar effect. So when we compare the frequency to this physics, we can now conclude that, okay, the frequency peak that we saw in the forces that we did not know the origin is connected to the separation of the boundary layer due to the strong adverse pressure gradient. And that is something that can only be achieved through a modal analysis, this kind of modal analysis, which is DMD. Also, another coherent structure that clearly shows the blade for the vortices behind the trailing edge of the blade, and the frequency is the runner blade passing frequency. And then we wanted to see if we can reconstruct the flow field through the data that we have, or if we can predict the future. So when we perform the DMD analysis, we have a trained model, and the model is trained based on data that we see in the first half of this graph, in the reconstruction part. So when we train the model based on these data, we can reproduce the data perfectly with close to zero error. You can see that the DMD reconstruction and the DS computation or the CFD simulation are precisely match each other. But can we predict the future? So here we call future, the data is not used for the DMD. The data is only presented as CFD simulation. We can see that at different points in the test section, we have different levels of accuracy. So closer, when we closer that we get to the runner, the accuracy of the prediction of the future is higher. But when we go far downstream, when we have a fully turbulent, disintegrated flow with a broad range of frequency, of course, that is a chaotic flow, and it's impossible to predict. So the chaotic nature of turbulence actually makes it very challenging, or probably impossible for data-driven methods to predict. So these results are published, or will be published very close in the future in the Physics of Fluids. The paper is accepted, but I think it will be online quite soon. So in the second part of this presentation, I want to talk about now how can we utilize artificial intelligence to control this instability, to help improve the lifetime of the machine. So here we are looking at deep reinforcement learning. Deep reinforcement learning, or reinforcement learning, is based on interaction of an agent with an environment. The agent usually observes the environment or state of the environment, then performs some action, and based on that action, it receives some reward. And through this mechanism, reinforcement learning learns how to perform complicated tasks. And well, DRL is simply a combination of deep learning and reinforcement learning. So the agent is actually a deep neural network. So deep reinforcement learning very recently has made its own way into fluid dynamics as well, and it has been used in a couple of applications. But what I'm interested in is that controlling instabilities through deep reinforcement learning. So what I did in this second part of this project is that I started developing a framework that we can use to kind of control the instabilities inside the flows. And I developed a framework, a coupled DRL CFD framework for active flow control. And then here, the DRL framework here you can see is a deep neural network. It senses the environment, it senses the CFD simulation, and then it creates an action and it receives a feedback. So in this particular case, I'm using TensorFlow and a coupled TensorFlow with OpenFOAM. And there are a lot of technical aspects to this framework and coupling that I would like to skip, but if you have any question, we can talk more about that. But one important issue that I spent a few months on that is that I parallelized the framework to be able to work with different CFD simulation at the same time. But by parallel, I don't mean paralleling each CFD simulation. That is of course used, but handling different CFD simulations at the same time. And is the parallel library MPI is used. The reason that I use the MPI here is that so we can support can have support from the distributed memory architecture, or simply when you have a cluster with different nodes. So I wanted to test this framework first and look at a very simple two-dimensional case. Of course, it's one can say that's far from what happens inside hydraulic turbines, but fundamentally, physically, what happens here is actually close to vortex drop. So vortex breakdown is the kind of the fundamental or kind of a basis for these kind of instabilities. So here we are looking at active flow control in a two-dimensional cylinder, vortex shedding behind that. And the actuator that I'm using to control this is a pair of synthetic jets on the top and bottom of this cylinder here. And you can see these blue dots are where I sense the environment, which is the pressure actually. And then I want to maximize this reward function. That basically means that we want to minimize drag and lift coefficients. So again, I will skip a lot of details, but I will just go right to the result. And we trained the model using 1,000 episodes, 1,000 CFD simulations, and then we evaluate the trained model in a deterministic mode. So here you see on the top, you see the vortex shedding, drag, and lift coefficient on the bottom. So at time 40, the controller kicks in. So now the controller starts to work, and you can see that through a pair of synthetic jets, we are actually been able to almost entirely eliminate the vortex shedding. You can see that when time continues, we get to a minimum drag coefficient that is very close to a drag coefficient when there is no vortex shedding. And the lift coefficient is actually very close to zero. That means that the trained model is able to successfully almost entirely remove the vortex shedding and reach a very stable condition. But then I moved on and to a three-dimensional case, and that's much more challenging. And here we're looking at a vortex shedding behind a three-dimensional cylinder at Reynolds number 150, and that is it's an expensive case. It's like 400,000 cells. It's relatively coarse, but we need to run this case for hundreds, but in this case, thousands of CFD simulations. So it's pretty expensive simulation. And here you can see again, it was expensive to create animation here. So I'm just showing snapshots. And you can see that not as perfect as the 2D case, but to a very large extent, we have been able to remove the vortex shedding behind this cylinder, and the drag coefficient. When I compare this drag to a case when we forcefully remove the vortex shedding through a symmetry boundary, then we can see the drag coefficient here is actually very close to what we have there. So again, successful controlling, but of course, not as perfect as in 2D. There are a lot of challenges in this case, and yeah, I'm still working on it. And the next step will be then how to really implement this in a hydraulic turbine, and that will also be a very challenging case, because in each safety simulation now we're talking about millions of cells, and then we need to run this simulation for a couple of hundreds or thousands number of simulations, and these are transient simulations, of course. So the efficiency of this whole framework is the main bottleneck that I'm now working on. Yeah, to conclude, the data-driven methods can provide novel insights into the physics. Specifically, I use DMD, and then I was able to extract physical phenomena in form of coherent structure and answer some questions that were unanswered before this kind of analysis. For instance, the origin of specific frequencies. And then we looked at deep reinforcement learning for controlling complex flow instabilities, and I developed a framework that is now working and verified on 2D and 3D cases. There are still works to do, mostly about the efficiency of this framework. Yeah, thanks to SVC and NICE for the allocating supercomputer facilities, and of course the open phone community. Yeah, thank you all for listening.
Thank you for presenting. All right, now we've reached the end of the presentations for today. And now I welcome Jonas Karlsson from Uniper into the discussion. And you've prepared some questions for Lars-Johan and Zaid. And after a quick introduction of yourself, you're very welcome to ask your questions.
Right. Thank you, Andrea. Thanks you for presenting me as an expert. Actually, I jumped into this because one of my colleagues, who is actually an expert, is home with a cold, so you have to bear with me in this. But also thank you both Lars-Johan and Zaid for your interesting presentations. And yeah, as Andrea said, my name is Jonas Karlsson, working within the technology development team at Sydkraft Hydropower, well, Uniper. And so my first question, actually, that's is for Lars-Johan.
Yes.
And since I've been part of extracting some of the input data for your research, we're a little bit interested to hear your take on the quality of this data and what kind of pre-processing you need to do before you can actually implement this data into your models, and how far off we actually can be running these models in production, let's say.
Yeah, I think that maybe that's the big question, how far off we are to make this in production. And as I said earlier, one of that we divide it into like different power regimes, and also separate the opening and closing of the data. That's because I want to be able to have a more static behavior in just a small part of the data. And in that way, I will need less data to train a model, because it does not have to handle as large variations that you would need to train if you have just all the data in one model. So that's the idea of that. And otherwise, I think to verify your models, you can always make an artificial faults and so on, but in the end, I think you need to try them on real faults to get like the real proof that they work. And for hydropower, we're working with quite long lifetimes and lifespans, so therefore we need quite a large amount of data to do that. Yeah, and in this case, we're also working with like a sample frequency of one sample every 10 minutes. And if you have a higher sample frequency, I was in a meeting here the other day, maybe you can be able to just pick out when we regulate the turbine. That could also be an idea. And we've been looking some at that before also, but yeah, so that can be also the way to go.
Exactly, because we sample all this process data quite. It's quite dense. If you say it's like we have a lot of data sets that are sampled every second, for example. So, but it's hard for us to actually just put a model on the data actually, because we have I think we have to like pre-process the data to shape the quality and stuff like that before it can actually be fed into a model. Yeah, as you have seen. Right, thank you. So another question, and this is both for Lars-Johan and Said. So what are the main parameters that you have observed that affect the process? I guess in both cases, power and head and runner opening and etc. That's dominant. But are there any other parameters that we should be aware of and that we should monitor even closer, maybe? For example, vibration measurements, HBU, pressures, and maybe in Said's case, it's pressures in the spiral case and maybe in the draft tube and stuff like that. What do you say, Lars-Johan? You have been more into process data, maybe.
Yeah, for me, but I'm like sitting on the other side. I don't. So I often want more different types of data to test with. So, for example, vibration data. I have been thinking that's quite hard to get hold of from turbines to work with. So that I don't know how beneficial it would be in a real scenario, but I think it would be very interesting to work with those kind of signals, as it's quite common to work with them in other fields also. So, and I know there are some turbines that are equipped with these sensors, yeah, also. But
Right.
maybe that wasn't an answer to your question, but
Yeah, but what about you, Said? You work mainly with the simulated data, I guess. But if we were about to take your research into the dark and wet world, like the reality, what data what data do you need for your what data do you consume or should be beneficial of?
So if we were to implement this controlling mechanism in real life on a real turbine, what we need is to kind of observe the state of environment, which means that we need to at each specific time when we want to make an action from the controller to control the instabilities to make the flow stabler, we need to observe the flow. So we need a lot of sensors inside the flow, and we are mostly interested inside the draft tube of flow. And the state could be anything, could be pressure, could be velocity. Of course, pressure is usually much more easier. It's much easier to measure in experiment than velocity. So I could say that pressure at the draft tube of the turbine and kind of a rather complete information about the flow. So, but again, a part of my research is on how to measure this, or how to sense this environment, this flow field, in a sparse way. So the least amount of sensors required to get the highest information that we need. So that is something that I will study in the future. So I cannot say now that how much sensor or where we should place them, but that is something that I will study in the future. But in general, yes, I need sensors. I need information about the pressure or about the flow, continuous information in time, actually.
And then you also need some kind of jets for controlling the flow in the draft tube as well. Is that right understood from my side? All right.
That is correct. Yeah. So here my main focus is on the deep reinforcement learning mechanism itself. So the actuator could be anything. Could be jet, could be pulsating jet, could be axial jet, could be any kind of additional geometry that is actively controlled, like blades or guide vanes or anything. But that could be anything, and the model will be able to train that actuator in a kind of an efficient way to control the flow.
Also, in your research, Said, is it possible to scale the force on the draft tube that the vortex rope actually is implying into the draft tube?
That's a very good question. I cannot answer that for now, because that is something that I'm also planning to do. So the main focus for me were having on the developing on the framework, but later I really want to see if this framework, which is trained on a modular scale, can be used on a real turbine on a full scale. That is something that I will see. Of course, if I would guess, is that no, we cannot just transfer the model to a real turbine. There needs to be some considerations, but there are a lot of methods like transfer learning and so on to actually train a neural network on a model and then use it in another situation. That is something that is in theory possible, but yeah, it needs a lot of research.
All right. Yeah, that's kind of interesting, because we have some units today that we can actually, on some at some loads, we can actually hear the vortex rope pounding in the draft tube. So that's quite interesting, and it's just in like specific load regimes. Could be like maybe like if you're running it at 1 power, and then you just increase the power with just maybe just 1% or something, then the vortex rope is disappear, or it's not pounding the draft tube.
Yeah,
that's quite interesting.
Good to know.
Right. So do we have time for a last question, Andrea?
Yes, we do.
All right, good. So what will happen next? What will happen with your research, Lasse-Johan? Are you done with your research, or how is the time schedule for your project?
Yeah, for my project, I'm pretty much halfway, but I'm far from done, if I say
All right.
so. Yeah, I'm trying to get more data to try these models, and I also have some upcoming projects that will look on other things inside the Kaplan turbines, mostly connected to condition monitoring. But yeah, maybe that's my project is in many different ways. You can look at many different things in the turbines. Yeah.
So, what about you, Said?
Yeah, so as I said, the main focus so far has been on fundamental research, and of course the framework is still a little bit far away from being actually used in a turbine. But the long-term research plan is to develop it for real turbine, real cases, and then try to control the flow field of instability inside drafting of a real turbine.